So this is a video I've been wanting to do for a little while. Case orientation fan testing. Case fan orientation testing, whatever. So the point is, and the goal of this video is to show you what your options are as far as case cooling, how you can orient your fans toward your desired result. And there's more than one answer. There are more than one ways to do this. It's like spreading thermal paste, you know? Everybody's got their method, and sometimes there can be a difference between one or the other. And I've got testing here on a system that is fairly conventional. So the board is an X870E carbon Wi-Fi 9800X3D 5070 Ti, and it's an AIO, a Lian Li Galahad 360. So this is a fairly conventional setup, not like my main rig, which is a hardline custom loop. And it's a bit difficult to get in and out of that thing, to switch the fans around. You have to take everything apart, and you just can't do it. So you'd think I would have smartened up. If I was going to start a channel, I'd have a rig where I could swap components in and out pretty easy, but I just wasn't thinking it because I just like my stuff to be pretty. But this one, this 9800X3D, I'm building it for somebody else, and it's much more of a standard build, and it's really super easy to get in there, change fans around, put them in a different direction, or add fans. So we have 4 basic test configurations. So nothing exotic here. This is going to correspond to what probably like 80% of you guys are going to be building. So you've got your bottom intake and your rear exhaust. That part didn't change. What changed was the side and the top. So I have 2 configurations in the more standard top exhaust. So that is bottom intake, side intake, top exhaust, rear exhaust. That's the standard one. And then I did a push-pull with that around the top radiator. The top radiator has its tubes feeding downward onto the CPU cold plate, down into the cold plate. And we're going to try sandwiching that radiator with 2 sets of fans, 120 fans. So 3 120 fans, 2 360s sandwiching that radiator, pushing air up into the radiator and with 1 set of fans, and then pulling it out of the radiator with the other, a push-pull configuration in that setup. And then we're going to switch it up and do bottom intake and top intake, side and rear exhaust. And then we're going to do that again with a pull-push configuration with the 3 fans at the very top above the radiator, pulling air into it and then pushing that cool air onto the VRMs from the radiator. So those are the 4 test setups. Again, easy to do, easy to set up, very simple build, the type of build that most people are doing. Very simple fan setup, maybe slightly exotic with the pull push and push pull, but basically something that anybody can do and is very easy to test. So I'm going to give you the numbers and show you what components are improved cooling wise by these various orientations. So let's really quickly review these metrics that we're testing. CPU CCD, that is the actual temperature of the CCD, the core complex die, and it's measuring the physical silicon where the cores live. It reflects real thermal behavior. Now, some other metrics that you'll find in hardware info for this chip, like say TCTL, might include offsets to regulate fan curves, so aren't necessarily representative of actual silicon temps, which this one is. And then you have the same thing for the IOD hotspot. Your IOD handles the memory controller, UCLK, Infinity Fabric, FCLK. Think of it sort of like when we discussed RAM in the OC Math Hack video and your errors when you error in Carhu when you're trying to overclock your RAM. we broke it down by fault domains. So which fault domains can you investigate when you have an error? You can go to core logic, which is the voltage that controls what's happening within that core, the operating voltage of the core of the component. And then you have your signal integrity voltages, like your VDDQs. And that is for disparate components on the system to communicate with each other via the traces along the motherboard. So for disparate components, to like CPU to communicate with RAM, etc. Now you can apply that same logic to CCD, which is your core logic, versus IOD, which is your signal integrity. So your IOD handles Infinity Fabric, memory controller, PCIe lanes, USB, SATA, basically all the disparate components that have to interact with each other. And these subsystems that the IOD handles never fully idle. The IOD never fully idles. Even when the CCD cores do idle, the IOD never does. So while the CCD can get hotter, the IOD is responsible for a good deal of thermal stress. And the coolers that are manufactured for this chip tend to focus on the CCD zone. It's also built on a less efficient process node, a 6 nanometer node, whereas the CCD is built on 4 nanometers, so it has a slightly lower thermal efficiency. Now, the CPU, VDDCR, VDD, VRM, SVI, 3, TFN, I'm not going to go over what all of those mean. You can kind of look it up. A lot of it's AMD protocol type stuff, but basically what it's telling you is that these temperatures are being read via telemetry and not via something passive like a diode. The first one I have listed here is for the core voltage for your CCD, which includes the 3D V-cache, and this is for powering it. So this is the VRM basically for the this is the VRM reading that's powering the CCD. Not basically, that's what it is. And the same is true right beneath it. That's the VRM powering, the reading for the VRM powering the IOD. So your SOC voltages are again within that signal integrity domain, Infinity Fabric, memory controller, etc. System. So this is measuring kind of your chipset heat soak. It measures a diode that is near the chipset. And then if you go down, you'll see chipset 2. Now that's the internal temperature from within the PCH die. So they both measure chipset temps. Chipset 2 get a little bit hotter. And chipset 2 actually, some users have reported that it gets very, very hot depending on your board. Some people are saying like they're getting like 90 there at idle or something crazy like that. So you might need to go in there, put an extra thermal pad or something to cover that chipset, which is something that you can do whenever you do a new build. Actually, I've done it, where you just go right in there, take the heat sink off, and just put thermal pads on it on the chipset before you even start the rest of your build. This is probably a pretty good thing to do. So MOSFETs are switching components in the VRM that regulate voltage to the CPU. They're cooled by heat sinks, which are affected by top fan orientation. High MOS temps can lead to voltage droop and throttling under load. So this is something to keep an eye on, as it could reduce your overclocking headroom. So if MOS temps climb, if the temps of this sensor climb while the CPU stays idle, it's not a sign of your cooler inefficiency. It's more of a sign of your VRM heat soak. So that's kind of interesting. If you understand these temps, it can help you troubleshoot certain weird edge issues that you might notice. This sensor is basically your VRM health monitor. SPD hub temperature, that's your DIMM module. So this reflects the airflow near the DIMMs. GPU temperature versus GPU memory junction temperature. So memory junction reports the hottest point inside the VRAM chips. As we'll discover later, this doesn't necessarily mean that it's always going to read hotter than your GPU temps. It just depends on what your stress test is doing. GPU temp is your average temperature across multiple thermal sensors, which are embedded in the GPU die. And the GPU memory junction temperature reads the sensors that are nanoscale sensors that are built using the same lithography that are used to build the transistors. So that's going to give you real-time thermal telemetry from inside the die. So I decided to take some readings of idle temperatures at ambient idle temperatures within the case from a thermistor cable plugged into the motherboard. Most motherboards have a place for these thermistor cables, and I thought I'd put it to use. The probe is right in the middle of the case, sort of being held up by the tubes going from the AIO, and it's measuring in between the graphics card and the CPU. So I thought it would be a decent enough place to get these ambient readings. And in both configurations, doubling the number of fans around the radiator actually decreased the performance. Fan quantity does not equal better airflow because you get turbulence as a result of a couple phenomena like back pressure, which is resistance that the airflow is going to encounter when it tries to move through a restrictive medium like a radiator. So this hurt temps in the push-pull and pull-push configurations. There are little eddies like mini whirlwinds that can form when the airflow is disrupted or if it collides with obstacles. Just the same way water swirls around a rock in a stream. These airflow vectors collide when two airstreams meet head-on or at conflicting angles. So it's important to remember that fan quantity does not necessarily equal better airflow. Also, idle behavior does not equal load behavior. They don't behave the same way. At idle, like one is not just like a hotter version of the other. At idle, the radiator's thermal demand is low and airflow saturation leads to heat retention and turbulence. Under load, the radiator's thermal mass increases, and the extra airflow from pull-push helps evacuate or push air in faster, which can overcome these saturation effects. So this radiator can get basically saturated to the point that you start to feel the slight turbulence of, say, fans being out of alignment, etc. And that saturation is overcome often under load. That's kind of the theory as to why this occurs and why the extra 3 fans aren't really helping with ambient idle temps. Okay, so let's go ahead and examine the results of the testing. Over there to the right, you'll see this is labeled as config 1. That is the standard configuration that everybody is going to recommend. They're all going to say, if you go to Reddit or whatever, or your PC building groups or whatever, they're all going to say bottom and side intake, top and rear exhaust. They're big on the top exhaust. Because they say heat rises. We're going to talk about that in a second. But so this is your standard configuration. Just make note of that. And since all conditions are relative, let's go ahead and compare that to another one. I have to show you in Excel because it's easier for me to change the chart. So this is config 2. Now, again, this is just the 3 fans on top, not the 6 fans surrounding the radiator. So no push-pull or pull-push here. And what you see here is that consistently across all the CPU and VRM temps, top intake is optimal. Also, that is true for the dim temperatures, where we're seeing right around the mid 50s in both those dim modules and kissing 60 for the top exhaust configuration. So top intake is where you want to be depending on your system. It's just one option. It has its pluses and minuses, but the pluses are illustrated pretty clearly here. It is going to help your CPU core temperatures, your VRM temperatures, your MOSFETs, which are near the VRM, near the power delivery stage in the motherboard. It's going to help your dim temperatures as well. But in a couple areas, it will not help. It will be suboptimal. As you can see in this chart, it is suboptimal at the PCH. Bottom and top intake floods the socket zone with fresh air, which cools the CPU, the VRMs, and the DIMMs as mentioned, but it disrupts GPU shroud airflow and recirculates heat near the PCH because of the way that graphics cards intake air from the fans and exhaust air through the sides, which then mingles in that PCH zone. So side and rear exhaust evacuate socket heat efficiently, but they leave the GPU and chipset in a warmer, more stagnant zone. So top intake is great for CPU temps, great for VRM, great for DIMMs, especially that's good if you're overclocking memory. Not so Guido with the PCH temps and the GPU temps. If we go over, and we're going to examine push-pull and pull-push also, but let's go ahead and go to the GPU temps and just focus on the standard configurations here. So again, what you're seeing here with config 1 being bottom intake, side intake, top and rear exhaust, that is better a little bit for your GPU temps. So what we're seeing here is getting around to the mid 60s in the memory junction temperature and kissing just 60 with config 1. It's config 2 a little bit higher, and the same is true for GPU temperature. Now, again, I mentioned this before, but memory junction temperature isn't always hotter than GPU core temperature. It really depends on the workload. Core heavy tests like OCCT won't necessarily heat up VRAM as much. It just depends on which tests you use and which OCCT tests you use, because OCCT is pretty configurable. You can set it up in a way to stress VRAM, and then you'll see junction temperatures creeping up higher than GPU average. But memory heavy loads can flip that delta. So, but if your junction temp never moves, now that's the red flag. That's when you know you've got a problem with the memory junction temperature sensor. But for this testing, that junction temperature responded dynamically to various loads and configurations. So it's not a problem here that it's actually lower. It just depends, again, on your workload. So now that we've established that the bottom intake, side intake, top exhaust, rear exhaust is better for GPU and PCH, and that the bottom and top intake plus side and rear exhaust configuration is better for everything else, let's go ahead and examine both of those variants in relation to their push-pull or pull-push configurations. So what we're seeing here is that all of the temperatures for the push-pull, again, this is config 1, so bottom and side intake, top and rear exhaust, all of the temperatures are lower with the dual sets of three 120 millimeter fans sandwiching the radiator, except for the CCD and the IOD. Isn't that interesting? So what could possibly explain that? Well, when you switch from that standard, that 3 fans on top, to push-pull, so 6 fans sandwiching the top rad, you're doing a couple things. You are improving airflow through the radiator. More fans means more air pulled out of the case. This helps remove heat from the VRMs, the DIMMs, and the PCH. So those temps go down. But those extra fans may pull air away from the CPU cooler's intake zone, and that can slightly reduce how much cool air reaches the CPU itself. So the CCD and IOD core temps go up a little, even though everything around them is cooler. So think of it like this. You got a campfire and you got a bunch of fans all over the place. So let's say you take a fan and you blow it directly onto the fire, which in this analogy is the CPU core. Now that's going to lower the temperature of the flame. But then you've got a bunch of other fans, like say you take like 6 fans and set them up to pull air away from the area. That's going to cool the surroundings, but the flame might burn slightly hotter because it's not getting direct airflow. So that push-pull configuration here in config 1 improves the ambient cooling. So that's great for VRMs and DIMMs and the chipset, but it can slightly reduce the direct cooling to the CPU die, causing a very slight temperature increase. Now, here's what's interesting. So all these others go down, and then the CPU and the IOD temps go up. Now let's go ahead and see what happens in config 2. This is bottom and top intake, side and rear exhaust. And look, it's the same phenomena. Now, the CPU and IOD temps are cooler. Almost everything is cooler in this configuration, as we've covered before, except for the PCH and the GPU. But look at that. The config 2 standard with the top intake and not the 6 fans around the radiator is slightly cooler at the CCD and IOD compared to its pull-push variant. So we explained it in config 1. What explains it in config 2? Well, what does that pull-push do? It pulls air through the radiator into the case. Now, the first set of fans pulls air through the rad, which does heat the air slightly, because you're talking about the liquid in the radiator, which is cooling the hot CPU, which is under load. And that warmed air is then pushed downward into the zone of the socket. So you're pushing warm air toward the CPU cooler. That second set of fans pushes the already warmed air toward the CPU cooler. And so that means that the CPU cooler is fed warmer intake air, which reduces slightly its ability to cool the CCD and IOD. The CCD and IOD rely on direct cooler airflow. So if the cooler is fed radiator warmed air, its efficiency will drop slightly. In all these other temps, we are seeing a slight decrease in both the pull-push and push-pull variants related to config 1 and config 2. So now let's examine the push-pull and pull-push variants of each configuration as they relate to GPU temperatures. So the longer bars here are config 2, as we've discussed. Bottom and top intake plus side and rear exhaust is worse for GPU temperatures than bottom and side intake plus top and rear exhaust. So config 1, better for the GPU than config 2. And if you go ahead and look at the pull-push variant of config 2, what you'll see is that it's slightly better. The config 2 produces the pull-push, the 6 these 6 fans around the radiator intaking air is slightly better in this configuration for your GPU temperatures, although this configuration itself, as mentioned, for GPU temperatures is inferior to top exhaust. But what's kind of interesting about this, if you look at the top exhaust configuration itself, check that out. The orange represents the push-pull. That is the 6 fans sandwiching the radiator, exhausting air. It's actually, and there's not much of a difference at all, we're talking less than 1 degree, but it's actually slightly worse. The push-pull variant of this configuration with top exhaust is slightly worse than just having the 3 fans. So why is this happening? Well, in this configuration, you have bottom and side intake, so that's where the cool air enters, and top and rear exhaust, where the hot air is evacuated. And in that push-pull variant, you've got 6 fans on the top radiator pulling air out of the case. So in the standard, just with the 3 fans attached to that radiator, you've got air from the bottom and side intake, which flows across the GPU shroud and then exits through the top and rear. And so the GPU gets a nice steady stream of cool air. Now, when you add 3 extra fans to sandwich that radiator, now the top fans, you've got 6 of them, so they pull harder, increasing the air extraction. And this creates a very strong upward airflow, which is good for the ambient temperatures in the case, but that airflow can intercept or redirect the cool air coming from the side intake. And the result is less cool air reaching the GPU shroud, and some gets pulled upward before it can cool the GPU. But again, what's most relevant here is just simply restating that config 1 with bottom and side intake and top and rear exhaust, represented here by the blue bar, is more optimal for GPU temperatures than config 2 with the top and bottom intake and side and rear exhaust. So to sum up this testing, I can say that bottom and side intake plus top and rear exhaust is better for the lower part of the case, for the GPU temps and the PCH temps. And for everything above it, like your CPU temps, your VRM and your DIMMs, your MOSFETs, those temperatures will improve with top intake. So bottom and top intake plus side and rear exhaust is going to be better for those temperatures. Now, which one of those options would I recommend? I can't make a recommendation because I don't know which one I'm going to do myself. I want to tune the CPU. I want to overclock the RAM. That would suggest top intake. On the other hand, I also want to mod the BIOS of this 5070 Ti and up its power limit from 300 watts to 330. I think it would benefit from having side intake in that case. So what do? As always, you cook to your taste. All I can do is supply the information. But I think we've gone a long way in dispelling the heat rises myth. I mean, we've pushed air around in a bunch of different configurations here, and you know, I'm not sure that heat rises has had anything to do with this testing. That is the principal reason that everyone recommends top exhaust. But I think that you can absolutely have all 3 top fans as intake. It just depends on what you want to do, how you want to configure the cooling in your case, and what components you want to overclock, and what you want to do with your GPU, what you want to do with your memory, how hot your memory runs, etc. It's all up to you. This is just supplying information for you. So test it yourself. You know, always, always, always test it yourself, because that's how you learn. Not from my recommendations. Don't take anything I say as gospel. Go out and test it yourself. That's how you know. So if you believe in that vision and you've enjoyed this content and you're looking forward to more 9800X3D testing, because again, we've done all the Intel stuff, we've overclocked, and we've tuned the memory, we've done the latency optimizations on the Intel system. Now we're going to apply all of those optimization suites onto the AMD X3D architecture. And if you're interested in that content, that will be the subject of the next few videos. Please like and subscribe. Thanks so much for joining me for this testing, and I'll see you in the next one.